Okay. So, we will come to the next topic, that is load frequency control. So, little bit I have told you just now, right. So, question is that load frequency control, because of the deregulation also certain things have changed, right, the concept has changed, but after making all this analysis for conventional scenario only, then little bit flavor I will give you regarding the deregulation, such that you will have a better understanding. So, here what generally brief something I have written, I will explain that an electric energy system, that means in general it is a power system, must be maintained at the desired operating level characterized by, one is the nominal your frequency, nominal system frequency, that means it will operate at 50 or 60 hertz system, right, there it should be operating, its voltage profile also should be good, and load flow configuration, right. So, it is kept in the nominal state, I mean this frequency, right, by close control of the real and reactive powers generated in the controllable sources of the system. That means, you have to control both real and reactive power, but later we will come to that, but frequency case it is a real power, right. So, basically that power system it is a huge network, right, and some power system, one group of power system is interconnected to another group of power system, or one power system is connected to another power system, or sometimes power system operating totally isolated way. So, different versions are there, right. So, question is that we have to maintain that your nominal system frequency, of course, under normal operating conditions, right. So, question is that generation changes must be made to match the load variation. That means, suppose when there is a change in load, suppose there is a increase of load. So, generation actually that power system actually chases the load, right. Sometimes we call it is a load following, generator chasing the load or following the load. So, it is a load following. So, because I mean when the load is increased, suppose all of a sudden a power demand has increased 100 megawatt. So, generators, whether it is a suppose if it is a thermal unit, that it cannot generate power 100 megawatt instantaneously, it takes some time. That means, some transient imbalance will occur between generation and load, because there will be shortage of generation and load has increased. So, some transient imbalance will be there. So, accordingly generation slowly and slowly will pick up the load. So, generation actually chases the load, sometimes we call load following, that generator is following the load, right. So, that is why generation changes must be made to match the load variation at the nominal conditions, if the nominal state is to be maintained, right. If we want to maintain its nominal state, then naturally the generation and load it should match, right. If it is not, then it will be obtained in some way, right, at the departure of the system frequency. We will come later. The load changes continuously, because in a power system that load will change continuously, I mean switch on switch off, it is going on apart, but we are not considering here any fault studies or anything, right. We are considering normal operating conditions, right. So, and the system generator responding to control impulses chases the load. That means, whenever there is a change in load, right. So, some mismatch will happen. So, in that case, so you have to have your what you call some load your what you call that your generation increase or decrease mechanism, something you have to check, right. So, the signal will go to that, right, because you have a speed governing system, right, and accordingly you have to adjust the generation will adjust the load. So, that is why responding to the control impulses, later I will come, chases the load with the transient imbalance of load and generation reflected in speed or frequency variation. Because if this is a question to you, I am putting it, you will answer it, that if real power increases, there will be a decrease in frequency and the decrease of the speed of the your motor your generator turbine set at the power system, right, because generator turbine coupled together. So, if real power changes, if load increases, I mean real power load increases, there will be a decrease in the speed, and that is decrease in frequency. So, decrease in speed of that turbine generator system, and if load decreases, the frequency or the speed will increase of the turbine generator system, because turbine and generator coupled together. Now, question is, my question is to you, it is very interesting question, you should answer, that if load increases, right, then frequency will fall, That means suppose machine was operating at your 50 hertz, say speed is generator speed is 3000 rpm at the your power station, generating power station, and turbine generator is coupled together, it is a huge mass, right. Now load has increased, so although machine will not lose synchronism, but that there will be decrease in the speed because load has increased. My question is, if load increases, speed decreases, if load decreases, speed increases, why it is happening, what is the technical reason? This is a question to you, this is the first question. Second question is that if load increases, the speed is falling, that is generator turbine mass rotating at 3000 rpm, speed decreases means there will be a loss of kinetic energy, right. My question is where that kinetic energy goes, right. So, this is second question. So, first question is if there is a change in load, there will be change in speed or frequency, right. So, why this happens? And second question is that if your load is increases, speed decreases, right, and if load decreases, speed increases. But my question is either of these you can answer, that if load decreases, increases, speed decreases, that means turbine generator mass speed is decreasing, right, because frequency decreases. So, there will be loss of kinetic energy because generator and turbine is a huge mass, where that kinetic energy goes, it cannot be vanished into the blue, right. So, this is a question, it is a physics type of question, but you should answer this, right. So, that is why chases the load with that, this answer you will write and send it to me through email. If it is correct, I will tell you, otherwise I will correct you, right. With the transient unbalance or imbalance occurs between the, I told you, between the generation and the load, there will be a transient imbalance. If the load increases, there is a change in load between generation, there will be difference between generation and load, right. So, for small perturbation, when I mean disturbance is very small, right, a mismatch in real power balance affects primarily the system frequency. Same concept that decoupled load flow you have used, no. So, almost same thing, but leaves the bus voltage magnitude essentially unaffected. So, if there is a small change in real power, then it will affect that your what you call the voltage angle, that means the frequency or hence the speed, that is omega, right, but leaves the bus voltage magnitude essentially unaffected of the system, that will be decoupled. Similarly, if there is a change in reactive power, mismatch in reactive power balance, it basically affects the bus voltage magnitude, but leaves the system frequency essentially unaffected. That means these two things are decoupled, that means real power frequency control and that reactive power voltage control, they are decoupled, right. So, that is why the real power frequency we call PF control, right, and the reactive power voltage we call QV control, it is magnitude written here, right. Problems are decoupled control problems for the all practical purposes, right. So, in any power system, it is a desirable feature to achieve better system frequency, better frequency constancy then is obtained by the speed governing system alone. Speed governing system will come at the beginning itself will come, right. In an interconnected power system, it is also desirable to maintain the tie line power flow at scheduled level irrespective of the load changes in an area. Just we will come to that, this thing detail will come, but the idea is something like this. Suppose you have one power system here, what is area 1 and area 2 later will come. Suppose this is one power system, it is connected by 3 phase tie line, of course, this is your area 2, right, and this is your, this is actually tie line, there is 3 phase line actually. Tie line means these two powers are interconnected or tied together, that is why you call tie line. So, it is a 3 phase line. Here voltage magnitude V1, V2 angle delta 2, V1 angle delta 1, and tie line power is flowing, right. So, this is 1, this is 2. So, power flow is P tie 1 2, and load is here, and generation is here, this is the generation coming out from this. So, basically generation is equal to this tie power plus this load, is schematic diagram. Suppose total load is showing like this. So, this is schematic diagram. So, it is that means this suppose these two areas are there, suppose power flowing from this direction to that direction, that means this area actually has some contact. Of course, you have some contact that at certain time you can buy power. If you are, of course, here if you are shortage of power, then this particular power system, so area means a power system, right, later we will come to the definition of that. This particular power system can buy power from this power system if they have sufficient spinning reserve capacity, right. So, question is that that in that case your what you call that it will draw power from this line. So, this is a p tie real power only showing, because our objective will be real power only, reactive power we will not study in this course, right. So, that means here Pg is the generation. If this is the Pg should be equal to the p tie 1 2 plus the load, right. So, and second thing is, suppose at a particular hour, suppose contract is 150 megawatt. So, it will draw 150 megawatt from this side, from this power system will draw 150 megawatt from this side. So, that is why your that it is also desirable to maintain the tie line power flow at schedule level irrespective of load changes in an area. If both the side loads are there, here also loads are there, right, here also loads are there, whatever load is changing this side or that side, it does not matter. If I have a contact that 150 megawatt I will draw, there will be it should maintain that, right. To accomplish this, it becomes necessary to automatically manipulate the operation of main steam valve or hydrogate. In the case of steam turbine, it will be steam valve, or you have to, or hydrogates, because if you open the steam valve, then more steam input will be there. If you try to close it, steam input will be less, right. Or hydrogates, if you open the hydrogate, more water input will be there to the your turbine, right. In the accordance with a suitable control strategy, because whether speed is decreasing or increasing, according to that it will receive the signal, and according to that valve will be closing or opening, or hydrogates for hydropower plant it will open or close, right, which in turn actually controls the real power output of electric generator. This way your electric output of electric generator will be controlled. But in this course I have no intention to consider the hydro turbine, right, only thermal one will consider. But one or two things regarding hydro turbine, actually in hydro turbine that you have a reservoir, right, you have a dam, you have a reservoir, and basically water you are travelling to the penstock to the turbine, right. In case of hydro turbine, actually we will not discuss there, but hydro turbine governor actually PID type governor, proportional integral derivative type governor, but that is not the thing here. In the case of hydro turbine, as the water is travelling through the penstock, so what happened that if suppose the load has increased, right. So, as soon as load has increased, that it is the signal will go to that hydrogate, and this thing, and hydrogates will open. As soon as that hydrogate opens, immediately water, instead of travelling to the turbine, actually because of the vacuum created inside the penstock, and water will be, there will be reverse flow of water. So, that means initially what happens for hydro power station, if load increases, initially generation decreases, right, for some moment, and after that it picks up, and this is called, actually as the water gate you open, that water will travel back in the instead of coming down. So, it is called actually water hammer effect, right. So, this will not be considered, and whenever we consider the hydro turbine model, actually it's become actually in the function of tan hyperbolic, but we make it first order transfer function, but I hope I will not consider that. It will be then all the things are simple, but if you do the simulation for hydro turbine, you will see that initially generation is negative, they are decreasing, and after that it takes off, right. Whereas thermal power plant, it will not happen. Another thing is, for hydro power plant, actually if demand, if load, for suppose a hydro power station is supplying load, suppose load demand has increased. So, hydro can quickly meet the load demand much faster than your what you call the thermal power plant, because hydro actually is your what I will say is constant and not that stringent like your steam power plant, right, because in the steam power plant you have boilers, economizer, many other parts, right. But in the case of hydro case, it picks up the generation very faster. Suppose 10 megawatt load has increased, and suddenly it can meet the demand very quickly, whereas in the case of steam valve it cannot that, because generation rate constant or limit. If you want that thermal power plant or steam turbine, right, like non-deheat or heat type turbine, if it is there, it will generate 100 megawatt in few seconds. It is not possible, it has some limit, right, or it has some constant. So, I mean it is, although it is a machine, it has some physical limit. So, it cannot generate power as fast as hydro, right. So, these are certain differences. So that is why that your to maintain that everything, frequency maintain, time power schedule maintaining, that you have to have some control mechanism. So, that the problem of therefore, The problem of controlling the real power output of electric generators in this way is termed as load frequency control or automatic generation control, right. So, I told you in the beginning that automatic generation control means, suppose 100 megawatt load demand has increased. Suppose you have 5 units, that 100 megawatt you share among 5 units such that your economic fuel cost will be economical or minimum, because 5 generators may have different fuel cost characteristic, and 100 megawatt you just see that how things are happening. Suppose one generator can give 19 megawatt, another maybe 23 megawatt, like this, instead of equal sharing. So, in that case you will find that your and accordingly you send the signal to each generator such that it will generate all this power, such that total your 100 megawatt will be yours generated. So, anyway, so that is economic load dispatch. Now, second thing is the basic generator control loop, right. So, in an interconnected power system, load frequency control, that is in short we call LFC, or automatic voltage regulator we call AVR equipment are installed for each generator, right. So, figure 1 gives a schematic diagram of the LFC loop and AVR loop. So, this is figure 1. So, this is your figure 1. Suppose this is your, say, this is a steam power plant. So, it is steam, or if it is your what you call here it is showing valve control mechanism, there will be maybe 2-3 stages of valve control mechanism will be there, but here it is not shown, right. We will take the simple thing. So, if it is a hydro, then it will be hydro gate, right, opening. So, it is a steam. Now, here it is your what you call, this is a turbine, shaft, turbine generator connect to the shaft, right, and this is the generator, and this is 3-phase line, right. So, giving the small changes delta PG, PD or delta your QD whatsoever, right. So, delta PG plus delta QG generation changes will be there, and this is here it will sense the frequency sensor is there. Tie line power also will be measured, it is delta F, tie line power will be measured, and LFC controller will be here, and output signal will be delta PC, and this will go to the valve control mechanism, whether valve will be open or valve will be closed, right. So, and this one, this side voltage sensor will be there, automatic voltage regulator will be there, and this is your excitation system, and this is that your generator field, and this is delta QCI, right. This is overall that schematic LFC and AVR of synchronous generator. This is together, this is a schematic diagram, but this AVR generator field excitation system, that is actually comes actually power system dynamics and control, that is beyond the scope, although looks here very simple there, right, but those things are not easy, you have to consider so many things, right. So, but our case is we will only consider that load frequency control, we will not consider this part, we will not consider this part. So, this is a schematic diagram as a whole for the system. Now, small changes in real power are mainly dependent on changes in rotor angle delta, right. This is very simple, and thus the frequency. The reactive power is mainly dependent on the voltage magnitude, that is on the generator excitation, that is this side, right, that is this side, excitation side, right. The excitation system time constant actually very small, much than the prime mover time constant. That means, and its transient decay is much faster and does not affect the LFC dynamics. Actually, that if you consider AVR loop, all these excitation system, its time constant is very small compared to the prime mover dynamics, right. So, if you even if you try to couple them, you will find that when that actually this LFC side transient action starts, right, by that time its transient decay is much faster, it will be finished in 2-3 seconds. So, there will be almost no effect on the LFC dynamics, right. So, that is why these two are people are treating as a this thing, or what you call as a separate thing, your real power frequency control and reactive power voltage control, right. Thus, the coupling between the LFC loop and the AVR loop is negligible, the better you avoid this, and the load frequency and excitation voltage controller are analyzed independently, they are separate, right, they are separate. So, with this your what you call, now we will come to the fundamentals of speed governing system, right. So, the basic concept of speed governing can be illustrated by considering an isolated your generating unit supplying a load as shown in figure 2. I will come to the figure 2, right. So, suppose you have isolated load means not interconnected, right. Suppose you have this is valve, If it is a steam plant, if it is a gate, hydro gate, then it is a hydropower plant, but general, that is why written steam or water. If it is steam, it is thermal power plant, water means it is hydropower plant, right. And this is turbine, and this is your what you call, this is a mechanical torque, this is electrical torque, P m is the mechanical power, and this is a generator. This is a schematic diagram, and this is the load, and this is the frequency or speed, this is the governor, right. So, speed actually sensed, this is turbine generator shaft, this is turbine generator shaft, speed can be sensed, right. So, this is generating supplying a local load, this is a load. So, T m all this thing, and P L is load power, everything is given. This is, so water means it is a hydropower plant for water, and steam for thermal. This is a simple schematic diagram, and for generator, your governor, turbine, generator, and the load, supplying an isolated load, right, isolated load. So, this is a schematic diagram, we will come to that later, right. Next is that isochronous governor. Isochronous governor means that it is a constant speed, your what you call isochronous meaning is the constant speed. So, an isochronous governor adjusts the turbine valve or gate to bring the frequency back to the nominal value, right. That means, it will try to bring your what you call, it will adjust the, I mean it will control actually. In the case of steam plant, it will be valve, or in the case of hydro plant, it will be hydro gate, right, to bring the frequency back to the normal your what you call nominal value. So, this is steam or water, same thing for thermal power plant, steam or hydro water, right. So, this is valve or gate, this is your turbine, this is P m, just now I have shown, this is your generator, this is electrical power output, right. This is going to your, just now I have shown this diagram, right. This is your P m, and this is electrical power output, not shown here, this is P e, right, P e. And what, whenever we will assume all these thing analysis, we will assume that turbine is a lossless, there is no loss, right. So, turbine is a lossless. So, in per unit, P m and P e all will remain same, right, it is a lossless. So, now from this this is a turbine generator shaft, this is P m, but speed can be sensed from here. So, this is a reference frequency, say f r, it may be omega r also, no problem, right. And this is that your frequency is sensed from this shaft, speed is sensed. So, you can put it in frequency form, this is plus, this is minus. So, delta f is equal to f minus f r, this is the change in frequency, right. And this is taking some constant, say minus k, this is an integrator, and output of this one, that is delta E, actually valve or gate position, actually it is the signal is coming here, it is controlling the valve or hydro gate, a steam valve in the case of steam power plant, or hydro gate in case of your hydropower plant. And this is the turbine, turbine may be non-heat turbine or your what you call heat turbine, only schematic basic thing will go for that, for turbine, right, and we will assume it is lossless, right. And this is valve in the case of steam valve, or gate position in the case of hydro gate. This is a schematic diagram of an isochronous governor, right, but this isochronous governor is your what you call is suitable for such kind of operation, where only it is your only one generator, and it is your what you call supplying your what you call load, right. If you have two generators, if one generator, two or n number of generators does not matter, but only one generator has to supply the load. If there are two generators, then there will be problem for isochronous governor, because you will set certain things, the reference frequency setting manually, right. In that case, when you set it for 2 or 3 generators, the human error may be there, right. So, it cannot be constant same. In that case, what will happen, this difference for one generator will be different, another generator it will be different. So, all the generators what will try, they will try to set that frequency to their reference value. So, there will be a fight among them, that is why isochronous governor is suitable for only one generating unit, right. Therefore, this is actually figure 3, this is figure 3, whatever I told I have written here for you. So, figure 3 actually shows the schematic diagram of an isochronous speed governing system, just I showed you. The measured frequency f or speed omega you can take also is compared with the reference frequency f r or reference speed omega r. So, the error signal equal to frequency deviation delta f or speed deviation delta omega is equal to omega minus omega r. It will be amplified and integrated to produce, is amplified means this gain is there, right, is amplified and integrated to produce a control signal delta E. This is the control signal delta E is produced, it is integrated, right. So, which actuates the main steam supply valves in the case of steam turbine or gates in the case of a hydro turbine, that means this diagram, in this diagram, right. Now, now an isochronous governor works very well when a generator is supplying an isolated load, or when only one generator in a multi generator system is required to really respond to changes in the load. I mean, one generator supplying load, it is fine for your multi generator, your isochronous governor. However, for load sharing between generators connected to the system, droop characteristic or speed regulation must be provided, right, otherwise it will create problem, right. So, that is why your what you call this isochronous governor suitable for supplying only one generator supplying the load, that is all. Now, governors with speed droop characteristic. Now, we have seen this one, but here we will add one for feedback path, right. So, governors with speed droop characteristic. Listen here, whatever governors this thing I will show, right, your what you call, it will be a it will be quite easy for you, right. So, this is same thing, steam valve or valve gate, this is turbine, right, this is shaft, right. This is to generator as usual, right. This was earlier there, but here it is plus minus, now it is minus delta F, it was there, here it is, so it is a delta F feedback is there. So, we have taken this minus k was there. So, here we have taken it is minus of delta F, and there is a feedback from here, it is minus r, and this now it is k, and it is integrator, right. So, then this is that your signal delta E. So, one feedback path is put it here, the regulation we call R is a speed droop characteristic, or your what you call the regulation parameter of the governor, right. So, this portion actually that your what you call governor part, right, this portion is the governor part. Now, when two are now regarding isochronous governor, when two or more generating units are connected to the same system, isochronous I told you isochronous governor cannot be used, since each generating unit would have to have precisely the same speed setting, right. Otherwise, precisely the same speed setting, it is difficult, manually you are doing it. If there is slight error, then there will be tug of war among the units, right. If two units are there, then between the units, otherwise they would fight each other, and each will try to control system frequency to its own setting, right. That is why isochronous governor is suitable only for your what you call that when one generator is supplying one load. Thank you very much.